So now that we know how to switch things on and off, we can look at the things that we might be controlling. Linear actuators like these allow you to create piston-like linear motions through having electric motors that will drive through gears or whatever drive technologies. A rotating element down here, which on a screw thread will allow this piston to be pushed out or pulled back in. And they come in a whole variety of sizes and strengths. Often there's a potentiometer inside to provide some feedback on the position so that you can drive the motor and you can watch the position until the motor gets to where you wanted it to. And there's another video from Progressive Automations that'll let you see some Arduino control elements on linear actuators. Servo motors are kind of cool. They combine the motor actuation with gearing down and a potentiometer circuit that allows you some control. So you can make motions like this by changing different angles. And you'll run a servo in the lab. The basic idea with a servo is at 1.5 millisecond pulse like this, that tells it to be right in the middle of its position. If the pulse gets longer, 2 milliseconds, it should move about 90 degrees over this way. Although we see in practice, it'll go to almost 2.5 milliseconds with most of our servos before they'll get fully 90 degrees this way. And then if the pulse is shorter, down towards 1 millisecond or even half a millisecond, it'll rotate from the center point up to about 90 degrees in the opposite direction. So by using a servo and controlling this pulse length, we can get angular motion and the servo will seek to the position that we tell it to.
Go for it.
We can use that kind of motion to actuate all sorts of things. In this instance, we're looking at an actuation on an installed door deadbolt lock with a servo up here that's just pulling strings. So this is just an example of the kinds of things that you can do with servos. And they're available in a wide variety of sizes, at a wide variety of prices, and a wide variety of strengths. Stepper motors allow you to control not just the fact that the motor moves, but just how far it's moved. So you can move in angular steps under digital control signals. And that way you can send out some raw signals on your digital input-output to control the stepper motor. Or you can get a separate stepper motor controller that will handle all those details, and you can communicate with I2C or SPI or another digital protocol. If you make multiple steps in a continuous motion, then you can simulate something that looks a lot like continuous rotational motion. And because you're controlling just how many steps you're going, you know exactly how many rotations the stepper motor has gone. So these work really well in open loop control situations to get you to a position you think you want to get to by just sending enough steps in the right order to get there. Solenoids are essentially just the actuator part of a relay. They've got a piston in the middle, an electromagnetic coil around the piston, and when we energize that coil, it'll push the piston in one direction or the other. Individual solenoids can just be used as usually fairly short throw mechanical actuators to push or pull on something, or they can be built into things like these solenoid operated valves, which you can fasten into a piping system and use to, for example, turn water on and off. Or you could have solenoids opening and closing locks. Anything you have that needs a small amount of linear motion. The disadvantage, again, these are inductive loads and you'll need to put a diode on them. But sometimes switching things on and off may not be enough. You may not just want to go from one position to another, or either on or off for a valve, or on or off for a light. You may want to be able to dim lights, or run motors at controllable, variable different speeds, or be able to reverse direction. The first step in meeting that goal is to think about pulse width modulation. And the idea here is that you can take your 0 to 5 volt signal and you can switch it on and off really quickly to approximate voltages in between. Now that switching on the Arduino Uno typically happens at about 500 hertz or faster, so it can be quite a quick on-off, much faster than you can see with your eye. So if we go to a 25% duty cycle, that would be an analog write value of 64 out of 256, and we'd be on for a quarter of the time and off for 3/4 of the time. On for a quarter of the time, off for 3/4 of the time. So it's spending a quarter of its time at 5 volts, 3/4 of its time at 0 volts. So the average would then be 1 1/4 volts. And for a lot of applications, they'll respond just as if this was a continuous DC 1 1/4 volts. LED lighting, DC motors, they all work very well with PWM. If we go to a 50% duty cycle, it'll be on and off half the time, and that'd be as if we had something close to a 2.5 volt DC output. And finally, we'll go through 75% duty cycle up to 100% duty cycle, and that allows us to go all the way from nothing happening, 0 speed on the motor, up to everything happening, full speed on the motor, or full brightness on the lighting. PWM isn't always enough to get the control that we're looking for. Sometimes we need an actual continuous analog DC voltage. And the best way to do that is with a digital to analog converter. And you can find lots of microcontrollers with processors that provide digital to analog converters. They're usually there to let you create an arbitrary voltage signal as a function of time to make sounds or music and things like that. So they usually come in pairs to allow you to create stereo sound. Now, if you wanted to get the same sort of an effect on an Uno, it's possible to use a capacitor and a resistor to get something that approximates a continuously variable DC value, as long as you don't want that DC value to change all that quickly. And this is the same approach that's used with switching power supplies to get variable voltage outputs on a switching power supply. So with a capacitor, we can smooth out that square wave and wind up with something that looks pretty close to a continuous voltage ramp here. And there's an example cited there. So everything that we learned before about transistors and our ability to switch things on and off with transistors, we can also use our transistors to switch things on and off very quickly. So we can use our PWM signal to switch the transistor to supply power to the motor on an oscillating basis, switching on and off with PWM. And that's the great advantage of using a transistor to control your load, is that you can switch this very quickly at electronic speeds. So in the case of the PWM, more than 500 hertz, where you couldn't switch a relay that fast. You'd wear it out very quickly. So the result is you can use PWM to control the speed of a motor or the brightness of a set of lights. If you're trying to control a motor, though, and you want to do anything much more interesting than turn it on, bring it up to speed, and take it back down again, for instance, you wanted to reverse it, or you wanted to make sure that it had a long enough life on the control electronics, or you don't want to remember how to size diodes and things, you can buy motor drivers. And these packaged motor drivers have MOSFET transistors on them with the diodes that you need, and additional monitoring circuitry that'll make it a lot easier to control your motor with outputs from your Arduino. So this side would have all of the control information that would come from the Arduino, and over here the outputs that would go to our motor, an input voltage and ground, and the two outputs to the motor that would allow us to speed it up, slow it down, reverse it, and not overstress the driving system. So I'd strongly recommend just about any time you're trying to drive a motor, you probably want to buy a custom motor driver circuit, or have somebody who works with you, an electrical engineer, design a custom motor driver circuit to meet the objectives of your particular application. Now, if you're trying to drive motors from an Arduino, using a motor driver shield, these are a couple of big motor driver ICs. This is a shield that can plug right on top of an Arduino Uno and control two separate motors with reasonably high motor currents. I believe this one is good for up to about 10 amps, but I'd have to check on that. So the result is you've got a package here that can be controlled directly from the Arduino Uno that'll bring a couple of quite large motors up to speed, slow them back down again, and allow you to reverse the direction on them. And we've used this particular shield in a bunch of practical linear actuator projects. Shields, the big advantage, you've all found out already that your wiring is probably where your prototype is going to fail. This one, there are no wires to connect. All the connections go right through the pins on the motor driver shield, straight into the sockets on the Arduino, and you don't have a whole lot of hooking up to do. So an enormous practical advantage for making your systems work. So now you've got a bunch of the background stuff where you can measure what's going on and set out to control your world. Now, to make that happen in software on the Arduino IDE, here's basically what you're going to have to do. You're going to have to decide what elements you want to control and how you want them to change in response to conditions. And then you're going to have to initialize whatever systems you have in the setup function. Then you'll measure what the conditions are, change your control outputs by using digital write or analog write to change what's going on the output pins. And then you'll just repeat that in the loop, and you'll keep on going around measuring the conditions and changing the outputs. And the limits on what you can do with that kind of approach are mostly associated with the limits on what you can conceive of controlling. We've already learned to measure a bunch of things. The outputs that you can use and the types of systems you can control with those outputs are, I hesitate to say infinite, but there are an awful lot of them. So you've now got the tools to control a lot of the practical systems that you're going to encounter in an engineering, particularly a mechanical engineering world. Your task now is to figure out what you can conceive of controlling as part of your designs.